Hello, this is my explanation for the second exam. I'm Victor Reyes, and here goes. We are given a cart on a critically damped spring where the conditions are at time t equals 0, the cart is in equilibrium position, and at that same time t equals 0, it is kicked in the positive direction with the initial velocity of v naught, which is equal to x dot at time equals 0. As we can see in this system, the, the spring has a spring constant k kicked to v naught at the rest position, which we can call x naught, and we can consider the frictional force bx dot at each position. Keep in mind, since this is a critically damped system, we let the what do you call this damping constant beta equal to the initial angular velocity, which is omega naught. So here we have to find the position xt for all subsequent times at a rest position x equals 0. So at xt equals 0, it is 0. And for the condition for b is the same, but we let x be x0, which is not equal to 0. And additionally, we have to get how far the cart is from equilibrium at a time tau naught, which is equal to 2 pi over the initial angular velocity. So we start with the solution where we find the the position formula, or the equation for the position of the spring. So let's start with the general equation of the spring system, which is the force, or m times the acceleration, is equal to negative kx minus vx dot, or this speed, and we divide all sides by m, where we let the square root of k over m be equal to the initial angular velocity, and the damping constant beta is equal to b over 2m, which makes this equation. And to generalize, x double dot plus 2 beta x dot plus uh, the omega naught squared x is equal to 0, where where uh, where the solution for this equation is x equals e to the alpha t, where alpha is an auxiliary variable, and here are the derivatives. So we get the auxiliary equation, alpha squared plus 2 alpha beta plus alpha omega naught squared is equal to 0, where we eliminate e. And since we have this auxiliary equation, we now need to find the value for alpha, which can be obtained using the quadratic formula, where we use the quadratic formula again, negative b plus minus square root of b squared minus 4ac over 2a, and we plug in 1 as a, 2 beta as b, and omega naught squared as c, and we get the final answer, negative b, which is equal to the alpha. We plug that into the solution, and hence we get the solution x with respect to time is equal to a constant c1 times e to the negative beta t. And since we need the second solution, we get the derivative with respect to a constant, and since then we get negative c1t equals a negative c1t e to the negative bt, and we can let negative c1 become a positive constant c2, where C2 t e to the negative beta t. And hence, we have the general solution for a critically damped spring, which is xt C1 e to the negative bt plus C2 t e to the negative bt, where again our condition is beta is equal to the initial angular velocity. For now, so now for the condition A, we suppose x at t equals 0 is equal to 0, and so x dot t equals to 0 is equal to v0. So for C1, we plug in 0, which gives both e's equal to 1. And since this term has 0, this becomes 0, leaving us with the answer C1 is equal to 0. For C2, we use the derivative x dot here, where x dot at t equals 0 is equal to v0. And since C1 is already 0, we can eliminate this term. And then we look for C2, which is this. Since t here is equal to 0, we eliminate this term, and this becomes 1. So C2 times 1 plus 0 means, which is equal to V0, means that the constant C2 is equal to V0, sorry. So the complete solution then is xt is equal to V0 t equals negative bt. Now for B, we suppose that at xt equals 0, we have the position x0 and at x dot t equals 0, we have the velocity v0, and we tackle C1, where eventually we get the similar to letter A, we get the value. But since at letter A we initially thought that xt equals 0 is equal to 0, this time we equate it to x0, which means that C1 in this particular case is x0. For C2, we do the same thing as in A, and since we have now we know now that C1 is not 0 but instead x0, we plug it in this solution here, and as you can see, we also derive t in this case, which comes out as negative C1 beta e to the negative beta 0, which is equal to 1. And so here we equate it to V0 is equal to negative x0 beta plus C2. So now we can conclude that C2 is equal to V0 plus x0 beta. So finally, the solution, and we can simplify this, is now xt is equal to e to the negative beta t times x0 1 plus beta t plus v0 t. And since we have another case where t is equal to tau naught, which is equal to 2 pi over omega naught, we plug that in here, where since in this condition, damping is not present, we switch the beta here to omega naught, which cancels it out. Hence, we are left with the solution x in time tau naught is equal to e to the negative 2 pi over, not over, but instead multiplied to x naught times 1 plus 2 pi plus 2 pi v naught over the angular velocity. So here we have the solution for letter A, where I use, instead of x with respect to t, I used y with respect to x to simulate this graph. And here is the general solution for letter B, and here's the specific solution for at time, which is equal to tau naught, where I changed the omega naught to b for simplicity, since they are equal. Here I use the constants v1, v0, which is just v, and the damping constant beta as b, and here k is the x position, the initial x position x naught. So as we can see, it is as expected. In critical damping, the motion as time propagates along the system eventually returns to zero in any case. Like we can change the value of v naught, and it will still have this same graph, even the damping constant. And as the damping constant increases, the position as it goes through time, the position of the cart always goes back to zero even quicker, and even the x position.